So further free radical substitution is kind of just the next step on from free radical substitution, as the name kind of suggests. So in free radical substitution, you've got your methane, react it with something, let's say chlorine, and what you make is chloromethane and HCl. Now, that looks like a nice clean reaction. It looks like that's something that would happen, and it does. However, think about what's actually going on in a real chemical world. You've got your beaker, and we'll call it a beaker. It probably won't be a beaker, but we'll call it a beaker. And that's where you put your methane and your chlorine in. You put some UV light to do the homolytic fission of the chlorine, and you're going to make the dichloromethane and HCl. In real life, you're still going to have some of the methane left over. You're still going to have some of the chlorine left over. And in your beaker, you're going to have a mixture of the chlorine, the methane, the chloromethane, and the HCl. All of that's going to be in your beaker. So, in the initiation step, we've still got our chlorine being broken apart to form two chloride radicals. And those chloride radicals still probably exist. It's unlikely they're all going to be used up in the termination steps of the free radical substitution. So, in our beaker where this big reaction's happening, we're starting off with CH4s. And we've also got some chlorine in there. But this reaction's taken place already. So some of the chlorine won't have been broken apart. Some of it will have. So we'll have some Cl radicals. We're also going to have some chloromethane. And all of this is in this beaker, and it's just a big mixture at the moment. So, these chloride radicals, yes, they could bump into another methane and will make chloromethane. That's fine. But what could also happen is they bump in to a CHCl3, one of the chloromethanes. And this is where we talk about further free radical substitution. So this time, rather than just substituting on one chlorine, in the propagation step, number 1, rather than having a methane react with a chloride radical, we're going to have a chloromethane react with a chloride radical. So this is called further free radical substitution because this reaction happened in free radical substitution. We made the chloromethane. And this is further free radical substitution because now we're substituting more chlorines onto what we made in the first free radical substitution step. So initiation step exactly the same. Propagation step, exactly the same thing's going to happen as happened in free radical substitution. So if you're not confident with the normal free radical substitution, go back and make sure you are confident with it. This Cl radical is going to break open one of the carbon-hydrogen bonds. The chlorine is going to break open the carbon-hydrogen bond and take the hydrogen off. So it's removed one of the hydrogens, so it goes down to CH2Cl, don't forget that Cl's there, plus HCl. And we put a dot on the carbon because that's where the unpaired electron is, so that's the radical. So if you think back to normal free radical substitution, we had methane plus Cl. It went down to CH3. We just removed one of the hydrogens and turned it into a radical. And the hydrogen went off with the chlorine. Same thing's happened here. The number of hydrogens gone down from 3 to 2. So exactly the same pattern, exactly the same steps are happening, just with now slightly more complicated looking molecules. So propagation step 2. That's when we have the radical that we formed in the first step. Is going to react with some more Cl2 that's also in our reaction mixture. And the CH2Cl radical, that's going to break open the Cl2 molecule. The chlorine's going to go onto the radical, and we're going to produce a Cl radical as well. So again, it's exactly the same process that happened in normal free radical substitution. So I've recreated the Cl radical, so it's still acting as a catalyst. And then the termination step, the one that we actually care about is going to be the CH2Cl radical plus the Cl radical to produce dichloromethane, bit of DCM. Really, really useful organic solvent. So if we wanted to write that as a full chemical equation, it would be CH3Cl plus Cl2 goes to CH2Cl2 plus HCl. So again, that's exactly the same as the initial reaction. You're reacting with one Cl, producing one HCl, producing one HCl. If we wanted to think about what happened from the very beginning, when we started with methane, how have we got to the dichloromethane, then our full reaction would be methane plus 2 Cl2s goes to the dichloromethane plus 2 HCl's. So the number of chlorine molecules you need to start with is same as the number of chlorines in the final molecule, and the number in front of the HCl is the same as the number of Cl2s that you've started off with. So one of the chlorines goes onto this molecule, one of the chlorines goes into the HCl. So that's further substitution, but there's no reason for it to stop here. So we could, if we wanted to, do the propagation steps, starting off with this CH2Cl2, which is now in our reaction mixture. And again, it would react with a chloride radical. It would take one of the hydrogens off of the dichloromethane to produce a radical, and we're making more of the HCl. That's why we always get the same number of HCl's being produced in the final reaction, because every time you put a chlorine onto the organic molecule, you make one HCl. So propagation step 2. We're using this CHCl2 radical, reacting it with chlorine to make CHCl3 and reforming the chloride radical. So now we've made trichloromethane. But once you've got trichloromethane, and again the termination step there would just be the CHCl2 radical plus a Cl radical, there's nothing to stop us now reacting that CHCl3 radical, that CHCl3 molecule, trichloromethane, with another chloride radical. And this time, the radical we're forming is just CCl3 because we're removing the last hydrogen, making more of HCl because we make that every time. So now we can get that CCl3 radical, react it with more of the chlorine in our reaction mixture to make CCl4, tetrachloromethane. Again, a really, really common and useful and quite dangerous organic solvent. So, when you've got your initial reaction mixture and you do free radical substitution, and you've made these chloride radicals in the initiation step, which never changes, you are making a mixture of chloromethane, dichloromethane, trichloromethane, and tetrachloromethane. You don't have that much control over what to make, but there is one simple thing you can do to try and control whether you get mostly chloromethane or whether you get mostly tetrachloromethane. If you go back to this reaction and you think about what it would be to form the tetrachloromethane, it has to be methane plus 4 Cl2s going to CCl4 plus 4 HCl's. So, if you want to make mostly tetrachloromethane, CCl4, you want to use a big excess of Cl2 because we need lots of the Cl2 to make CCl4. So if you want to make lots of CCl4, tetrachloromethane or carbon tet, you want to use an excess of Cl2. If you want to make mostly just a single chloromethane, you want to stop there being more chlorines for it to react with, and in your reaction mixture, once you've done this first step of free radical substitution and made the chloromethane, you don't want there to be any more chlorine around. So to do that, you need a massive excess of methane. So to make mostly the CCl4, big excess of chlorine. To make mostly the CH3Cl, you want a big excess of the methane, because then there won't be many. It's not that there won't be many CH3Cls. There will just be any chloride radicals which are still in this mixture are more likely to bump into another methane molecule than they are into a chloromethane molecule. And if you bump into a methane molecule, you're going to make chloromethane rather than dichloromethane.